Okay, hello everybody, and today we're going to solve this problem. It asks us to find all the solutions to the following equation: x to the n plus 1 minus x plus 1 to the n equals 2001, where x and n are positive integers, so from the natural numbers. And this was asked on the Putnam exam from 2001, obviously. And now we're going to solve it. So first of all, notice that 2001 is divisible by 3. So you know this thing will also be divisible by 3. And when you try some values, if you for x can be 0, 1 or 2 modulo 3. Well, 0 won't work, because then this will be divisible by 3, but this wouldn't, and 2 will also not work, because then this part will be 0 or divisible by 3 and this part won't. So you already see that x has to be congruent to 1 modulo 3. And furthermore, if x is equal to 1 modulo 3, and then we see that this part will be congruent to 1. So this part has to be congruent to 1 modulo 3 without the negative sign. Let's write that down. And so if x is congruent to 1 modulo 3, we know 1 will be congruent by moving this to the other side, so 2 to the n modulo 3. And well, 2 is congruent to negative 1 modulo 3. That will be maybe a little bit easier to see, but this implies that n has to be even, because otherwise this part would be congruent to 2. So we not only know that x is congruent to 1 modulo 3, but also that n is congruent to 0 modulo 2. So those are already two quite important facts we've discovered about x and n. Okay, now let's do some further analysis. Now I want to look at the following thing. So we have x to the n plus 1 minus x plus 1 to the n. And well, this was 2001, but now we're going to add 1. This will be equal to 2002. But notice that this part will be divisible by x. There are different ways of seeing this. So for example, if you use the binomial theorem of this, you'll get a constant term of -1, and by adding 1 we remove the constant term, so this will always be divisible by x. Or when you're going to look modulo x, this part will disappear, and this will just be 1 to the nth power, which is going to be 1 modulo x, and then -1 plus 1 will be congruent to 0. So either way you look at it, you see that x divides this, so x divides 2002. Well, 2002, you can work that out. It's equal to 2 times 7 times 11 times 13. And we also knew that x was congruent to 1 modulo 3. So you can, and you know all the divisors, we actually only care about the positive divisors because x is a positive integer. We see that x is going to be from this set: 7, 13, 22, 91, 154, 286, or 2002. So that's nice, but there are still a lot of options. Well, there's another thing we can say about this thing. Well, notice what happens if we look at it at modulo x plus 1, and this thing will disappear, so we still have 2002 will be congruent to this, while this thing disappears. So we have x to the n plus 1 plus 1 modulo x plus 1, but x was also x will be congruent to -1 modulo x plus 1. So we have -1 to the n plus 1 power, and n was even, as we saw up here. So this thing will be odd, and we'll just get 0. So also x plus 1 is a divisor of 2002. And if you use that for in this set, you check if you increase x by 1, will it still divide our number 2002? And you'll see that there only is going to be one option, which is 13. So that's nice. And you see our equation becomes 13 to the n plus 1 power minus 14 to the nth power equals 2001. So that's nice. We've found one of the two numbers, but we still have to find n. And for that, let's first suppose n was even. That's also a thing that we know. So let's look at this equation. Let's first suppose that n is going to be bigger than or equal to 4, because then we can do a neat trick. We can look at this equation modulo 8, and we see that 13 to the n plus 1 and then minus 14 to the n, but 14 is a factor of 2, and when n is greater than or equal to 4, we know we have at least 4 factors of 2 in here, so this will definitely be going to be congruent to 0 modulo 8, which is the modulo we want to look at this. So it's congruent to 2001, which is congruent to 1 mod 8. But on the other hand, 13 to the n plus 1 is going to be congruent to, well, 5 to the n plus 1. We're working still modulo 8. When we congruent to 5 times 5 to the n. But n was even. Let's here suppose n is equal to 2 to the k. And we can take this to become 5 times 5 to the 2 and then to the n. Here it should have been a k. And we can write it as n is 2k and then take this 2 inside. Well, 5 to the second power, 5 squared, is equal to 25. When you mod it out, mod 8, you'll get exactly 1. So 1 to the kth power will be going to be congruent to 1 modulo 8. So this is congruent to 5 mod 8. But here we see that this same thing is congruent to 1 and congruent to 5 modulo 8. Well, 1 is not equal to congruent to 5 modulo 8. So we can totally rule out all of these options. Well, if n can't be greater than or equal to 4, there's only one option, because n is even and n is an integer, a positive integer. The only case we're left with is going to be n equals 2. But we also already knew that x was equal to 13. So, and we want to check is what is 13 to the third power minus 14 squared. Well, this is going to be 2197 minus 196, which definitely equals 2001. So there we found our solution. N equals 2 x equals 13.